Hey, this is Dr. B here, and let's talk about the background material you might need to understand nuclear medicine. That means we'll be talking about nuclear processes only, not chemical processes. Chemical processes involve the formation of a new substance. So does a nuclear process, but it's through combining or breaking apart of the nucleus, whereas normal chemistry, the nucleus is not affected. So, nuclear medicine will rely on those types of atoms which can have unstable nuclei. Sometimes the term radioactive is used, and we'll talk about how you can predict which ones might. We can use this for medical visualization. Oftentimes, gamma detectors are used, as well as treatment using nuclear substances known as radionuclides. Okay, the background that's going to follow is mostly about nuclear chemistry. Let's begin by considering what an atom is. It is a substance which contains, as you've probably heard, protons, neutrons, and electrons. We assign these following charges to them: positive for the proton and negative for the electron. That simply means there'll be an electrostatic attraction between the two. Opposite charges attract. And neutrons which have no charge. The electron is interestingly considered to be an elementary matter particle. There it is right here. If you look at the standard model, which, boy, there's nothing standard about this, of the universe. What are the smallest particles in the universe? We see that the electron is one of them. Protons and neutrons, no. They are further subdivided. A proton consists of some up quarks, some down quarks, and some gluons. Neutrons also in differing amounts. And the standard model consists of 12 of these matter particles shown here, as well as 5 of these force particles. These are known as bosons. The matter particles are known as fermions. There is so much more detail you can go into here, but I think it's interesting to note that there's a lot of elementary particles, and there's a lot of overlap between matter and energy. The electron itself is believed to have a dual nature, part matter, part energy. I think of that as what happens when things get really small. So, if you're going to work with unstable nuclei, and nuclear medicine does, these are radionuclides. They have a few common properties. In general, they have too many neutrons, meaning that if you compare the number of neutrons to protons, it is greater than 1.5. This is used as a predictive tool that you have an unstable nucleus. Anytime you have an element greater than 83 protons, it is every isotope of every one of those elements are unstable. As an interesting factoid, it's also the case with technetium, which I believe is 42 protons. Every single isotope, for reasons that are not well understood, are unstable isotopes. They fall apart quickly. Isotopes seem to be somewhat random in nature. They are different for all of the elements, the isotope abundance. Okay, so they're going to fall apart. How are they going to fall apart? Let's take a look at the possible decay particles. They might fall apart and give off this substance here. This is a helium-2+ nucleus, right? It is helium with no electrons. That's the charge there. That means it's missing the 2 electrons that a helium atom has. This is its atomic number, just the number of protons. It has to be 2, otherwise it's not helium. This is the mass number, which is protons plus neutrons, which means you have to do the math, 4 minus 2, to get the number of neutrons. So that is known as a alpha particle, perhaps one of the commonest forms of nuclear decay. It might also just spit out this substance, which looks like an electron, but it's not. How can it have a -1 in terms of the number of protons? This symbolizes for this particle that it actually has a proton that turned into a neutron, hence you lost a proton. So that's some unusual nomenclature, but try to get comfortable with that. They call that a beta particle. Proton turns into a neutron, and there you go. You could also be a gamma particle, which really isn't a particle at all. No protons, no neutrons, pure form of energy, gamma rays. It may turn into this type of substance, which also is not an electron, because it looks like you're gaining a proton. So a neutron gets turned into a proton, plus it forms an electron. This is known as a positron. your average type of electron at all. It's kind of like an electron with a wrong charge. This substance is straightforward. No protons, one neutron, let's call it a neutron. One proton, no neutrons, let's call it a proton. Those are the common nuclear decay particles. We're showing them up here in a little more detail. So there's your nucleus. It could give off a proton. This is known as proton emission, which is relatively rare. It could give off a neutron. This is typically goes along with fission, and neutron sources can be used to initiate a nuclear process. If, after all, nuclear decay begins with having too much neutrons, a neutron source could accelerate that process. Similarly, a neutron capture substance, which also exists, can act for brakes during nuclear fission process. So maybe you can see that as a way to understand how you can control, the nuclear fission power plant in Waterford, Connecticut, which is about 20 miles from my house. You could also have electron decay where also a neutron is converted to a proton, so it spits out an electron. However, a neutron converted to a proton, we call that beta emission. Pretty weird, right? We could have the proton converted into a neutron and also an electron form, but they call that a positron with the plus symbol. Sometimes they call this beta plus emission. I think more commonly they just call it positron emission. You can give off an alpha particle, that's alpha decay, very common. Or you can give off some energy in the form of gamma rays, that's gamma emission. The rate of this decay is called a first order process. It's one of the early things you learn in a kinetics study, and therefore it's just proportional to time. It's some kind of a constant, and a big number for that constant K would mean a relatively short half-life, meaning fast nuclear decay, and the concentration is given as N. Without showing the math, you can figure out how long it takes for half of the substance to decompose, and this is the formula that's used. The half-life for these first-order processes is equal to 0.693 divided by the rate constant. This is a common source for questions on an exam, where they oftentimes just give you one of these and you determine the other. This is some background on nuclear medicine.